video. All right. So if you remember from last time, we had the DC amplifier. Then we have our DC motor. We have our disk. Then there was an output, right? Which is here is actual speed. Then our input, it was speed setting through a voltage source, right? Now, what has been added to this system? You see this tachometer, right, connected to DC. So here, this tachometer is our sensor that reads the output. So what happens here is we are going to say now we can manipulate the output. So our desired speed now is our reference input. Now we have a reference, right? So that reference here is a desired speed. After this junction, it becomes an error, right? That goes into our controller. Now, from this controller, so DC motor was an actuator, right? If you remember, and then the disk was our process, things that being done in that system. So now here, after the controller, here, this is a variable that is suitable for the actuator. So I'm going to write a commanded variable. So now this, after the controller, whatever signal comes out, the actuator understands it. Before the controller, it was just a difference in speed, right? Just a number, hey, 5 more RPM. The controller then raises it, and then it converts it to voltage that actuator understands. Then that, now we close the loop, that's a closed loop system. So this is showing the block diagram. We don't exactly know what are the equation of motion of any of these subsystems, right? We don't know the properties of them right now. We can show them as blocks, and we say that this is a block diagram. Here, the direction of the signals are really important, and if you have a summing junction, it is important if your signal is going in positive or negative sign into them. And today we will talk about the terminology and a little bit of algebra of these, of the block diagrams, and we will get a more complex block diagram and simplify to a simple one. When I say simplify, I mean input, system, output. We're gonna convert that, all right? We're not touching anything and not talking about transfer functions yet. We're just gonna say, we're gonna call it A, B, C, D, and work with that. Once we learn about transfer function, then we can actually write them and then talk about their stability because we have more information, all right? So if you wanted to know like how we are building up, that's basically the process that I'm following. All right, so this was your class participation. I can give you some of the examples like of my solution for these. I haven't posted that, but they will basically follow the same structure here. If you remember, we solved an error of an open loop system. So we are going to find the error for a closed loop system. So that's the same system that we did last time. The only difference is here, the gain is set to 10. And now we have our controller and the plant is as it was before. You had the controller, but you didn't have any signal going back, right? It was not a feedback closed loop system. Now, to calculate the error, so you might see something like this in your exam, maybe, or homework. When we calculate the error should talk about input and output, right? So the signals you want to see in it should be input and output. So your input is R, right? The reference input. Your output is Y. So the idea is we are going to get an expression that has R and Y in it, right? So I'm going to call it YCL, so Y closed loop, and R is my reference input. You see that there is a U. The U is the controller input, right? So don't get these two confused. U controls the actuator, that something comes out of the controller. Now from the plant, your YCA, you can write, so one way to do this, at the end, we want to find the error, which is input minus output. So here you're getting omega or W, what was W?
Environment.
The process noise, noise from the environment. So 0.5 W minus U, so you have U minus 0.5 W times 10 is your YCL. So it's going to be 10 times 0.5 W minus U, and I can write that as 5, well, actually is U minus W. There you go. U minus 0.5. So this is going to be 10U minus 5. All right, so that's one part. So I found the YCL from my plant. Now, for the controller, I can find U from this controller. U is going to be, so this is R, here is YCL. So this is R minus YCL times 10 is U, right? So I can write U is 10 times R minus YCL over equals to. So reference input minus output. Now combining them, I'm going to get YCL, basically subbing for U, so I can only have R and YCL. So I can say YCL is equal to 10. So what I'm doing is subbing this here, right? 10 times minus 5. I already did that. Minus 5W. So this becomes 100 R minus 10 YCL. If you were in my robotic class, we did this, if you remember. Minus 50W. All right, so now what do I have here? I have YCL on this side, YCL on this side, right? So you remember that I needed to find the error, right? And it should be input and output. I have something else in there, W, right? What should I do with that W? That's the noise from the environment, right? The process noise. Usually when you solve, yes.
If we're subbing U into what would the 10 multiply up to W?
100, yeah. So the W is the noise. So you usually have an idea of what kind of noise you have. You either have it, you measure it, or you will assign a function, like a random noise or white noise to it. So your W will have a value for you to know what input gives you the desired output. So for now, we're going to leave the W as it is, making sure everything else is based on R and YCL. All right. So here, if we bring, so YCL plus 100 YCL is 100 R minus 50W. Then if you solve for YCL, you're going to have 100 R or 101 R, 101 minus 50 over 101. All right, so this is our YCL. Now error is input, reference input minus YCL, which is R minus, be careful with the signs, 50, 101 W, so it's R minus 100 over 101 R plus 50 over 101 W. Nope, what happened? All right, so then simplify. This will give you E, or error is R over 101 plus 5W over 101. Now, if you remember, now if we have a value for our noise, let's say that is a controller for a car, you have 1% elevation, or you hit a bump that you know what kind of disturbance it will create. You plug that number for W and you see what error gives you. So you can anticipate how your system will behave. Right, yes. It's 5W. Yeah, that's what I wrote. But this one is 50.
In the beginning, when you sub in new times, the 10 is very.
This one. This one is 5.
Yeah. Yeah, but the 10 outside there is only.
Oh. Here. No. Yes. Okay, I see. Like here. Yeah. All right. I'll check the math. But the final answer is correct though. All right. Good. I'll check the process, but the idea is check the output, right, from the plant. Check the controller output U from the controller side. You want to make sure everything's based on your reference input and your output. If you have process noise or even noise from the sensor, we leave it as it is. We don't replace it because we know that we will have values for them if we want to tune our controller, use our controller. All right. Okay. So for this part, the bonus part, I'll talk about it if we had time, but the bonus part is about linearization. So if you have a nonlinear system, what do we do to it? So it becomes linear and we can use it. All right, so I'll talk about it if you had time today. Now, while I'll change the lecture, go on Carmen and do the roll call. There's a question that you need to answer. Yeah, it opens at 3 and closes at 4. I'm going to. No, let's keep that in. Let's see how many of you believe that robots are bad. How many of you stopped the GitHub, not GitHub, what is it, Grubhub robot outside? Raise your hand, be honest. Okay, just remember, rise of robot, they're gonna come after you. I don't do that, I believe in karma. Huh? They have an Instagram? Oh, I will follow, no, I didn't know that. Is it just Grubhub?
No, OSU likes robot.
OSU robots?
OSU robot.
Okay, yeah. Sweet. Great, something extra that I will not work and check. Yeah, I needed that.
I got one of them like.
They are, yeah. I will, thank you. Another thing to not work. Yeah. All right, is everybody in? So you have to do this roll call. I'll check that and then I'll inform the registrar just to drop your name if it's not there. That's all. Okay. How many of you had signals before this class or have at the same time? Ooh, you're gonna be bored today. But you can do the examples very easy and then homework is a piece of cake. All right, so let's do that. I'm gonna show the homework because I already posted. I'm gonna talk about like how my homeworks work. So you go to the module, homework open today, and you have until February 2nd. So It's 2 weeks from now. So my homeworks usually, when you open them, it was like, what? You haven't talked about it. Why there's a question? So first of all, that's where you find them. And then I included what I'm looking for. So you'll see here that question 1 talk about LTI system. So tell me if it says linear, if it's not linear, non-linear, right? And if it's linear, is it time invariant or not? So you want to check both of them, and then you have to show. So if it holds one, goes the second one, the third one. So you have to show your work, otherwise you would not get points. Then question 2 is finding a transfer function. We haven't talked about it. We're going to talk about it today, right? Then this question is kind of similar, so you would know it by Friday. But then there's this question that says that draw a block diagram of this using signal flow graph, and we haven't talked about it. So we will talk about it next week, but this is due on February 2nd. So I give you the homework ahead of time, so you can kind of look and say what part of the lecture you're going to be evaluated on. So I might talk about a lot of things, but there are a few that I will ask you questions. So you want to pay special attention to those ones, right? Yes.
So does that mean like if we see content in the lecture that isn't in the homework, we should not expect that content to be part of the exam?
Good question. The content that is in the homework and is on class participations, definitely going to be in the homework, right? And you'll see my in the exam. And my exam are a good example of my homeworks. If you had class with me, you know that you won't get surprised. But the other thing is my exam, the first part always has conceptual question, how much you understood the topic, right? So that it is in the lecture. I talked about it. I probably also talked about it or asked in class participation, because I think if you don't understand the fundamentals or the basic or the concept of something, it doesn't matter if you can solve a problem, because you just learned that one problem. You get an A, but then you really don't know why we're using transfer functions, right? I want to make sure you understand that, plus you do your problems. So the first part always going to be true, false, simple one-word answers or really simple calculation about concept. Then the problems you'll have seen them. It's not going to be out of this word. All right. You have your book. I don't know how many of you got the book. You'll see that if you follow the syllabus, I'm not following chapter 1, 2, 3, 4, 5. I think the book didn't do a good job. So I created my lecture based on how things make sense. So I might jump from one chapter to another, and just because it will make sense to talk about it right now. All right. I'll try to give you the book chapter to follow for the problems if you want to practice more. If you couldn't find a problem to practice, come to me. I'll give you some extra problems. All right. I usually have extra problems. I will solve it and put on Carmen for you to practice, so you can use that to help you for the exam. All right. Okay. So this is your homework. You have until February 2nd, and you cannot work with anyone. It's individual, but you can use office hours. All right. So stop sharing from there. Oh, I can't do that. Now I have to share from here. All right. But if you already had system and signal, you probably can solve all of that. Go ahead, do it. You can submit early. That's fine. Don't be late though. Yeah, late is not acceptable. All right, so this is an example of a complicated-ish sample system. And you see that I just said system. We don't still know what's in them, right? We're learning about their algebra and how they're configured. Our goal for now is to make that complicated system to a very simplified input system output. Remember, all of them are LTI, linear time invariant. So everything we said about transfer function, that if you had the impulse input, you basically know the output to the various signals applies, right? So block diagram terminology, if you see a line with an arrow, that's a signal. If you see a block, that's your system, right? Now, if you have two blocks in series, you can combine them, and using convolution, you can show that the combination would be, for example, here G1 times G2, right? But we call them these cascaded blocks. They are back to back in series. You have input signal, a signal from G1 goes to G2, and then your output signal. They could have, they could come into a summation point, a circle with signs. The signs are important. The direction of the arrow is important for the math. You also have takeoff points. So takeoff points here, if I have signal A, if I take a signal, it will be the same signal if nothing else applies. Why? Because this line itself is 1, right? So it's basically, here is 1, A, 1. So this is 1 times A equal A. So the math holds, all right? If you have a block that you have 2 signals going into it without going through a summation point, that is not a transfer function. You have 2 input, 1 output, right? That's something else. So all of your block will have 1 input, 1 output for now because we are working on CISO system, single input, single output, all right? We do have blocks that look like this. They're different. You see when we go to MATLAB and Simulink, you'll see them. They're mocks. Path, we have 2 kind of path, forward and parallel. So forward, you can see here, so following the arrows, I can start from a point, follow, go to the output, from input to the output. There are different ways you see that for this system that I can have forward path. Parallel path, if you start from a starting point, doesn't have to be your input, start from a starting point, go to the output or to an end point. There is another path that goes forward from that same starting point to your endpoint. That's called parallel. The reason I'm talking about this terminology is that later we will use this terminology to apply algebra to them. So we combine parallel differently than, for example, feedback. All right. So being able to recognize them is helpful. Now, so these are the different examples of parallel. You can start very short. You could go from 1 point, go back, come here, and this. So these 2 are parallel. So again, the idea is to combine them, right? So we have different loops. Loops that starts from 1 point and goes back to that starting point, but following the direction of arrows. You cannot go against the arrow. You're following the signal. You can have cascaded loops that are they have the same start and the same end. You can have interlock loop that they have 1 or 2 blocks similar in common, right? And you also have non-touching loop. So some of them like kind of, you can remember from 2020 also, you had same things, I think, like loops and branches. And yeah, I know 2020 is not the best memory, but 3 kind of loops. When we are in combining them, it's important which one they are. Now, the algebra, if 2 of them are in series, you multiply them. So the new block is the multiplication of the other 2. If they are forward parallel path, you can add them, right? So the block that replaces those 2 will be the addition of them, and then the input signal and output signal stays the same. So we need to know where we started and where we ended. And you see that here, YS is our output, is US. Now YS will be US times GS HS, right? So again, the idea is we want to find what's the output considering what was the input. So when we simplify our signal, we want to get to this point. What is the equation for that? Because how can I write the transfer function of the system based on this? Do you remember? What's the transfer function of that system on top? No, we are in S domain. So we say transfer function. Transfer function is the S domain. It's not in time domain. Okay. So now, so those blocks are a system, right? There is a transfer function in there, and the representation is GS. So GS is equal to something, right? We don't know what it is. Fine. Now, the other block is HS, and our input, also in S domain, is US. Now, I want to know what's the transfer function for the system. How do I write it based on information?
The input over output, so you have
Output over input.
oh yeah, so YS over US.
Yeah. So from here, right? This goes there. So GS, HS. That's why we simplify, because now I can write the transfer function of this system. Now, why is this good? Do you remember transfer functions? Could we look at the denominator of transfer function and say things about our system? Great, you don't know. No, it's fine. I just want to know if you know. That's awesome. Okay, next week gonna be interesting. All right. So for now, the goal is this, to find the output based on the input, and then we can go one step later and write the transfer function. Simply y over we grab the input from the other side. So we are gonna, for now, focus on creating this guy. So talked about these two. Now, do you remember we had takeoff points and summation points? These two are a little bit more challenging, let's say, when you're dealing with them. You just have to remember that if you have a takeoff point, you usually want to move them around so you can combine your blocks. So you basically want to make everything look either in series, parallel, or you'll see in feedback loop. So if you want to move a takeoff block, takeoff point, so if it is on the right side and you go to the left side, you add this value of this block to this signal, right? The idea is you want to know what ys is, right? So ys from here is us times gs, correct? And takeoff point is basically the same signal, you just took a wire, you connected a wire. Now, when we move this block, the resulting ys should be the same on both branches. So now you see here, ys is us gs, that was fine. Now in this new one, your ys is again us gs, right? So this operation that we did has to hold the value of our output, right? So same transfer function, same value for our signal. If you're moving a summing junction, if you're going, so you're in front of it, you're moving it behind, then you will have 1 over the value of that block. So you're moving over that block. And you can prove this. I leave it to you, it's in my annotated version. So you can follow if you didn't know how to do it, if you forgot. Good on these two. So these two are probably what you want to always pay attention, which way you're moving. And then removing a feedback path. So here, if you have GS in the top of the feedback, so in the signal forward path, and then HS is in the feedback loop, you can write GS, the one on top, over 1 plus GHS. Now, if this was a negative feedback, this becomes positive. If this was positive, this becomes a negative. So now you see that YS is this block times US. If I wanted to write the transfer function that we will see later would be G over 1 plus GH. This is a filter. So we're gonna get there because that transfer function could be things that we want to apply or control our system with. All right. So you can either remember this or you can drive it if you forgot. All right. So to drive that, I'm going to do it quickly. So here you have ES, your error is going to be US minus, because this is the signal, which is YS times HS. Correct? So this is the error. I can also say that in YS from the top, the forward path is going to be ES times GS. Right? So I can write that. Now, if you sub ES here, you can basically write everything based on Y, G, and H in your input U and get the transfer function. So I'm going to do that. YS is US minus YS HS multiplied by this GS. So you write US. Now, this is Y, this is Y. And remember that we want to make sure that U also appears in our equation. So solving for YS, I'm going to write the final solution. but you can feel free to move this one over there is ys plus ys hs. So it's ys us times gs over 1 plus hsgs. So now you see that this box is gonna be this box after simplification. Right, so we simplified that. So if you forgot how to do the feedback loop, it's very quick, you can write it. Also, I usually let you bring your cheat sheet, so you can put that in your cheat sheet. But since we use this a lot, it's good to remember it if you don't know it. Good. Shall we continue? If I'm going fast, let me know, because I think most of you know these things. So that's why I'm going a little bit faster. But if you needed me to slow down, let me know. All right, so rule of thumbs. After this, you're going to solve 2 examples. All right. So rule of thumbs. First, look for all the blocks that are in series. Look for all of them that are in parallel. Simplify them as quickly as possible. Then look for blocks that are a feedback loop, because you also know what the math is, right? Once you run out of all of them, you have to move the takeoff point and summation point. The takeoff point, usually we can shift them to the right, so kind of create series. And for the summation point, we can shift them to the left. Yes.
Okay, sorry. We don't point to it. So like, it's not five, so you five.
So this is U, right? It's a signal. If I grab a wire, so this was a wire, right? If I grab and connect a wire to it, think about voltage. So let's say this was 3 volt. If I grab a wire and connect it to it, there's nothing in between. When I measure, how many volt is that? The second one, 3 volts, right? If I do that, 3 volt. So that's basically means I'm grabbing a wire, I'm connected to a sensor, I'm connecting to an actuator, I'm connecting to a fan, right? So basically using the same value. So that's takeoff point. So usually like no manipulation. The summation point, you're having 2 signals coming into each other. So 3 plus 2, or they can leave also. Good. All right. So pay attention to takeoff, because it's different from summation point. Even both summation point plus and plus, right? Then once you don't have any of those anymore that you can work with, go back to step 1, because you use this 4 and 5 to create parallel and series and feedback. Then continue until you only have one gigantic system in between your input and your output. We are good? Have you done this before? Hopefully, yes. Yeah. Okay, there's a quick reminder. Solve this. For now, write down the steps. So make sure that you remember. So you have 2 examples. One is this one, the other one is a slightly more work. So I'll give you about probably 5 minutes for this one. I'll walk around and look at what you're doing. Did you find anything? Oh, all of them are responsible.
Yeah, can you find out?
Okay, thank you. All right, so we're just having extra zeros. All right.
Well,
Oh, yeah. All right, for this one, I'm going to, if you're still working, you can work. I'm going to write the steps so you can see how I would solve it. And then once you learn, you don't have to show the steps, but I suggest do it for the first time if you haven't done this before. So I'm looking for parallel series. This is in series, right? So this is from step one. So step one, find series. So that's what it says. Find in series and simplify. So it would be. So what I'm doing is I drop the S. It's easier to write. So you can do that as well. So this is my input plus minus. I can write BC. This is Y. Takeoff point, basically same signal, goes to B here, goes back. All right, I've done that. Step two, do I have anything in parallel? No. Go to step three, feedback loop. Yes, so this is a feedback loop, right? Because it starts from here, following the signal, goes here, this is a negative feedback. So I remember that I can write the top BC over 1 plus the feedback times the forward, the parallel path, the forward path, sorry. So I'm gonna write it in different color, U, A, then I am basically combining my feedback, which is BC 1 plus BCD, and then this is Y. All right, now 4 and 5, take off and summation. No, so I can go to 6, go to step 1, go to 1. 1 is, do I have anything in series? Yes, combine them. U, A, B, C over 1 plus B, C, D, that is Y. So can I simplify more? No, I reached to input a gigantic block output, right? I'm done. So I can write output is equal to A, B, C over 1 plus B, C, D, U. If I was asked to write what's the output, if I was asked what's the transfer function, I would say U over Y over U, which is this block is the transfer function. So the transfer function of this system is this gigantic block. All right. If you're done with this and you understand how it works, go and solve the next problem. That one is a little bit longer. You should be able to do it in 6 minutes. If not, you can just follow the annotated version after that. I think the most issues I see in block reduction is that it seems simple, you do it in your head and you make a mathematical mistake, like a plus or minus, and the final. This one is a little bit. So your homework, you can do question 1, 2. You could do question 3 if you know how transfer functions work. If not, we'll talk about it. Yeah, Friday we have a class presentation. Or you want to let me know? You don't want to. That's the sad part. That's the ugly part of this. And thank God, God created MATLAB because you can use MATLAB for this. But we are gonna go through the pain so we can appreciate our software. But yeah, for exam, since you don't have access to MATLAB, you're gonna do it by hand and for homework. But you can check your homework with MATLAB, but you can't just do it with MATLAB. All right. We'll talk about that. All right. So if you have to leave, you can. Otherwise, like I'm going to write this. It's going to be in my annotated lecture as well, but it's almost class time. Just a show of hand. As a class, do you need more practice? If you think you need more practice on examples of block diagram, raise your hand. I'm preparing Friday's lecture for this. Just want to make sure how many examples I should bring. Don't care who raised their hand, right? Just raise your hand if you think you need more help, more example. Okay, so I'll put 2-3 example for Friday, but I will include a little bit of transfer function so we can jump. All right. Yeah. Always ask question. There is no stupid question. Don't worry if nobody else has a question, only you. All right. They might not thought about it. Might not have thought about it. So, okay. So what I'm going to do here, I'm going to look for all the series. There's none. I'm going to look for parallels. There is none that goes from one point to another. And then there's no feedback. So the only thing I have to do is either move a takeoff point or summation point. So I'm going to start from a takeoff point. So this is a takeoff point, right? If I move it over here, then I will have 2 in series, right? And then, so I'm going to draw this. If I move that over, becomes this, right? So this is now a parallel path to this. And I also created 2 series. So now I can simplify this. But don't forget, when we move a takeoff point, we have to add that, manipulate that block, right? Because we are moving our signal over a block. So for this, Fs would be, because I'm moving it this way, would be multiplied by 1/c. So as a help, I added this appendix that has all of these, how to move, take off from right to left, left to right, summation from right to left, left to right, and the other one. So you want to look at these 6 example and have it with you. But moving this will create, so it basically, here you will have 1/c. So it kind of cancels out what you just did. You moved over c, right? But so you divide by 1/c, so c times 1/c is 1. Basically, that's what we're trying to do. Now I can combine them. This is F/c. This one is BC. This one is D, right? Minus, so I haven't, so now I know these 2 are in parallel. So for parallel, I can add them, right? Yes. I'm gonna go there. See what this is. And then you have the summation point. So what you will end up with. So there is no one way to solve the block diagram reduction, right? So this is one way. If you need to leave, you can. I'll keep solving and it will be part of the recorded lecture. So this is Y, and here is your A and U, and we have E. Now from here, these 2 parallel, and I can combine them, and it becomes BC. This is parallel F/c plus D. Now I see that feedback loop. That's E, that goes here, Y. So this is a feedback loop. I can simplify that. This is A. I'm gonna have A, BC 1 plus BCF over C plus D, E, and U. So now this is basically solved because these two are in series. And when you put the two series together, you have a feedback loop. And when you write is really ugly, I'll try to give you exam questions that are simple, but your homework might not be as simple. It might take a little bit of time to solve. So this is feedback. And these two are in series. So I can write this as BCA 1 plus BCF over C plus D. You can also simplify here. So this is BF plus BCD. You can do that to just help yourself to make this simpler for yourself. It's E in the feedback loop. That's U plus minus. So you will, so now is this gigantic block on the numerator over this 1 plus gigantic plus block times E, right? And you'll be done. Now, I'm gonna cheat and give you the shorter version, but in the exam, you have to do that last part, and if you didn't simplify, it's okay, all right? BF plus A, B, C, E. So that's your gigantic block. Y, U, you're done. That's the end of it, all right? There are different ways of solving, but you will have to end up with the same transfer function. All right?